Streams like these can show how elements change their grouping across time. On a timeline from left to right, you can follow individual elements. These elements, for example, might represent researchers working together on different topics. Over time, they shift their research focus and collaborators. While this representation is easy to understand and applicable in many scenarios, it comes with an inherent limitation. The limitation is, at each time step, the elements need to form a partition. But what if an element does not just belong to one group, but multiple groups? For instance, researchers might work on different topics simultaneously. This cannot be properly represented as a sequence of partitions. Instead, we need to visualize overlapping sets, which are dynamic. They change across time. Set visualization has already been discussed in various papers. However, surprisingly, there's only little research on visualizing dynamic sets. The recent state-of-the-art report describes it as one of the main open problems of set visualization. It is particularly challenging as time adds another dimension to an already challenging visualization problem. Nevertheless, few approaches have been published on the topic already, but none of them focuses on visualizing the evolving sets as streams that you can follow on a timeline. Our considerations for designing an approach like this were the following. We want to provide an overview across all temporal changes. For this, we need a timeline representation. Changes should be easy to follow. Streams provide a basis for this. In addition, we want to compare subgroups of elements and which temporal changes they undergo. The approach we suggest is called set streams. To be able to represent the sets as streams, we first need to find a solution how we deal with the overlaps. The idea is to split the overlapping sets into exclusive intersections. These intersections are shown here as rows with combinations of colors, indicating which of the three original sets contribute to them. We do not consider all possible intersections, but only the non-empty ones. That is why the combination of purple and green is missing in this example. It is important to note that these intersections are exclusive, in the sense that an element can only be represented in one of them, namely the most specialized one. To give you an example, if an element belongs to all three sets, it will be part of the exclusive intersection of the three sets, but not part of any other exclusive intersection. These exclusive intersections are organized as rows and form the basis of the visualization layout of set streams. The specific encoding, marked boxes representing the sets, is inspired from upset, a tabular visualization approach for static sets. Now we can represent the changing sets as streams on a timeline. The time steps are arranged as columns from left to right. The elements, as they are only part of at most one exclusive intersection per time steps, can flow between the groups much like shown in the initial example. Elements that are new in one time step are represented as inflows from the top. Similarly, there are outflows of elements that are not considered in the following time steps at the bottom. Histograms at the top show how many elements are contained in the exclusive one-set intersections, two-set intersections, and three-set intersections. With this base layout, we already achieve our goals of getting a temporal overview and being able to follow changes across time. Still missing in the base layout is support for comparing groups of elements. For this, we introduce an interactive querying and selection mechanism. Two groups can be selected and compared. Orange and green color represents the groups. You can specify in a simple sentence-like format which set operation you want to use, on which participating sets, and based on which time step. This selection can now be shown as an overlay on the timeline representation. We use black color for those elements that are contained in both selection groups. As an alternative to using the query form, it is possible to simply click on a node or edge in the timeline. A respective query selection is then activated to select the contained elements. So this is the central timeline-based visualization of set streams. But the full interface of our implemented solution, which you can see here, has some more views and features. To prioritize different base sets or characteristics, as well as to simplify the vertical layout, we provide various options for sorting and aggregating the rows. Moreover, there is a list of elements at the right side. To quickly find an element of interest, you can use the search field. Colored markers in the list reflect the current selection and can be used to inspect details. You can also click on one element, which then becomes highlighted as an overlay of the timeline representation in yellow. To demonstrate how to work with the approach and tool, I want to showcase an application example. It investigates how the expertise of researchers from a community evolves with respect to different subfields. We take the main authors of the visualization community as a sample. They form the elements. Now we want to learn how they shift their focus between the subfields of scientific visualization, information visualization, and visual analytics. The subfields hence represent the sets. We can extract this information from the publications at the EuroVis conference. We consider the time span from 1990 to 2015 and divide the publications by conference tracks: SciVis, InfoVis, and VAST. Please note that the original VIS conference is considered here as a predecessor of SciVis. In set streams, the data looks like this. The rows show authors that made contributions to only one track, to two tracks, or all three. The columns show timestamps of a span of 3 years each. We have selected more than 1 year here to stabilize the movements. First, investigating the general structure, we clearly observe the origin of the conference series in the VIS/SciVis track. The InfoVis track is branching in the mid-90s and about 10 years later the VAST track. The introduction of the VAST track was successful in the sense that the established researchers represented in this dataset also started publishing in this track right from the beginning. However, nobody immediately switched to only publishing at the VAST track, but instead new people came in that started with the VAST track only. From 2005, in general, the many diagonal connections between the nodes show good mobility between the tracks. Also, mainly in the last 2 time steps, all combinations of tracks are non-empty and populated by multiple authors. This shows that the tracks do not separate the community. In the period of 2005 to 2010, the situation was clearly not as balanced between the tracks yet, but still more focused on SciVis/VIS. Second, we contrast particular groups of authors. For instance, we can compare the group of early contributors and the group of recent generalists. The groups only share one researcher, Jack van Wyk. Many of the early contributors are still active in the community, as only few orange edges leading out at the bottom. These authors have spread across all combinations of tracks. Further, it is interesting to note that the recent generalists all started their contributions to the conference with contributions to Cyvis/Vis. The green incoming edges all lead to the exclusive Cyvis/Vis node. You can find 2 more application examples in the paper. One on studying the evolution of the Linux project and its main contributors, and the other one on analyzing the training phase of a multi-labeling image classification algorithm. So this is our approach called set streams. It visualizes dynamic changes in set structures, providing a temporal overview, supporting to follow changes across time, and to compare groups of elements. You can check out our tool online or find more details on the approach in our paper.